Hi friends, welcome to this channel, and in this video we are going to look at problem 872, leaf similar trees. This is a daily challenge problem. So in this video we are going to present several solution formats based on in-order traversal. We can use both recursive format or iterative format. So first we are going to quickly digest the problem statement, and then we look at the coding. So here we are given two binary trees, right? So we want to check if the two trees are leaf similar. So by leaf similar, it means that if the leaf value sequence is the same. The leaf value sequence basically is you can get these leaf values and then form a list or array, right? So here, this one, for example, in example 1, so the leaf sequence is 6, 7, 4, 9, 8. So similarly, in this tree, rooted at this 3. So it's 6, 7, 4, and 9, 8. So notice that, so these two trees are leaf similar, but their structure is not similar, right? So in example 2, so the two leaf sequences are different. So the first one corresponds to 2, 3, while the second one corresponds to 3, 2, right? So here we can see the constraints. So first, the number of nodes in each tree will be in the range given by the closed interval, say 1 and 200. And similarly, the values also in this is in the range including 0, and the upper bound is 200. So in other words, the constraints tell us that this problem is actually a small size problem. So with that said, we are ready to look at the logic. So in order to compare if two trees are leaf similar, so we need to get the leaf sequence, right? So for the leaf sequence, in order to get it, actually we can do in-order traversal. So this is the main observation, right? So if you traverse the tree in a in-order order. So you're going to get, say for example, if you do this, you're going to take 6, 5, 7, 2, 4, then 3, and then 9, 1, 8, right? The order of the leaves are the same as we read from left to right. So in other words, we need to modify the typical in-order traversal algorithm. So that's basically our main guiding principle. So with that said, we are ready to look at coding. So I'm going to present several formats of code just for practicing purpose, also for pedagogical purpose. The first one, I'm going to use recursion. So I'm going to mimic the in-order traversal. The reason for in-order traversal is actually very simple, right? So if you do a, let me maybe write a hyperfunction. So in order. So you're given the root. Then if not root, so we can return just empty, right? So otherwise we can return in order root left. Then plus you can choose to return the tree node, or you can just return its value. So for example, if we return its value, it's going to look like this, in order root right. So this is the standard in-order traversal algorithm in recursive format. But here we want to just get all those, right? Then we're going to filter out those that are not the leaves. So we are going to do this. So here, notice that this is the typical in-order traversal. I'm going to comment this out just for comparison purpose, right? Then I just define, I still call it in order, but I want to take put the problem logic here. So first, if not root, or root is none, so this is the stop condition or base case. So we're going to return an empty list. So our goal is to get the leaf sequence. So then we want to check another base case or stop condition, that is not root left and not root right. This basically means that the tree is a single single node tree. So this root is also a leaf. So in this case, I'm going to return, because for this problem, we don't need to compare the tree nodes. We just pay attention to the values. So we can return root value. So otherwise, what we're going to return, so if this condition, the complement is that either the tree has left subtree or right subtree. In other words, the root itself for sure is not a leaf. So in this case, we just need to return in order root left plus self in order root right. So if you compare this part and this function, you can see that, so this is essentially a in-order traversal, but we don't return this, for example, root value, right? And we add a additional check, that is the leaf condition, right? If it's a leaf, we are going to include that root value in the return list. So this will serve our purpose. So once we have this hyperfunction, so you can write as a method within this class, or you can write a nested function within this method leaf similar. So we just need to call this function twice for each of the two roots, and then we can do the return. So for this problem, we just need to return not self, because we write a nested function. So root 1, let's see if it equals in order root 2. So this actually forms a solution to this problem. So now let's do a test. In order, so let's see. Oh, I see. In order. So here it's not a method, it's a nested function. Now let's test again. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So this is the one way to write this. So here I want to copy this one, and I still use recursion, but I want to use a more verbose way. So here I directly write this one, and then we directly get the leaf value sequence, and then we compare. So if you are not very familiar with this sort process, you can do a very verbose one. You can first do in-order traversal. You get all the nodes, and then you do filter. You filter out those leaves, those nodes which are not leaves. So here we do it automatically due to this logic. If you look at the code together, right? So this forms the filtering logic. But if you want to write in a robust way, it's also doable. Let's see, define in order. So we have a root, and then what I'm going to do is that if not root, I'm going to essentially copy this part. So let me copy this one. But in order to do filtering, I don't return the value. I return the nodes themselves. And then we can, because the return format, we can do filtering. So we can do filtering. The reason that we can do like this way is due to the fact that the number of nodes is very small, right? If you do a product, 200 times 200 is bounded by 40,000. So in other words, storing this thing takes some space, right? So it's still small because of the problem size. So now we get leaf value sequence 1. So it's going to be something like this. So let me write it directly. So for node value, for node in order, say root 1, right? So we want to make sure this node is not a it's a leaf, right? So in other words, the condition is if not node left and not node, right? In other words, it has no children or no subtrees. So this is for the first tree, and then we copy this one and change the 1 to be 2, right? So we get the second leaf value sequence. We just need to compare them. So let's see, leaf value sequence 1 equals leaf value sequence 2, right? So now let's do a test. So I'm going to change this one to be version v1, and then let's do a test. Yeah, it passes one example. So now let's look at the generic case. Yeah, it passes all the cases, but still very fast. So here, the reason we can do this filtering is due to the fact that what we returned on node is a tree node. That's why we return node, not values. So this way actually takes a lot of space to store this result. So these two solutions are based on recursion or recursive format. Let me copy this function signature and change this to be a version v2. So I want to write a version v3 based on iterative format. So actually we know how to write in-order traversal in iterative format. Let me quickly write this a function like this, and then I'm going to add problem logic instead, right? Let's see, I'm going to write a in-order traversal. So actually we have in our channel, so we have a lot of solution videos for traversals related to in-order, post-order, and pre-order, or zigzag or level order traversal. You're welcome to check out those if you feel those might be helpful. So here first I'm going to write a in-order traversal algorithm, and then I'm going to modify and add the problem logic here, which will let you see how we can build a solution based on some previous knowledge or previous experience. So here I'm going to initialize a result variable. So this list is going to store the values if we do in-order traversal for this tree, right? So here, let's maybe we can just first I'm going to initialize a stack. So then I'm going to set a current node. This is the current root. Then basically the standard while loop of iteration, right? While result or stack, right? So not result, while current. So if one of this is true, then we are going to check current, while current, right? So if you think of this example, if you want to do in-order traversal, the first value you are going to get is 6, right? So then you can say currently you're here, you want to move to the very left, right? So while current, then we are going to stack append current. So in other words, later after we visit C5, so we need to go to their right children. So then we are going to move to the left, current left. So after this while loop, then the current will be null, right? But we saved the 6 in the tail or at the top of the stack. Then what we're going to do is to pop this current, pop, right? So once you pop this value, typically you are going to say append current value. And then what you are going to do, so you are going to move current to current right, right? So then you return the result. So this solution format does not take into consideration of the problem logic. We just do a vanilla in-order traversal. Let's check that. So let's say print in-order. So let's say root 1. So here in the first example, where this actually this one, right? So you will see we get 6, 5, 7, 2, 4, 3, 9, 1, 8, right? So this is the vanilla in-order traversal. So let me copy this one and comment out this one. I'll put it here for your convenience, right? So you can see. So now I want to add problem logic, right? So now, so that's up to here, right? So we do a pop operation. So we don't directly append the value. So, but we do a test. So we add problem logic here. So what's the problem logic? So if we want to save it, so actually we want to check, make sure this current is a leaf node. In other words, if not current left and not current right. So this means the current is a leaf. Then we're going to save this value to the output. And this way, we're going to give you the leaf value sequence. So now let's do a test again, right? So again, I'm going to print out this. So another root 1. So it should give us 67498. 67498. All right. So now we know this. Then we just need to do the return, right? So return another this one, and then let's check if it's equals to the leaf value sequence for the second tree, that is root 2. So with that done, now let's do a test. Yeah, it passes one example. So now let's look at the generic case. Yeah, it passes all the cases. I guess up to now we finished our plan, that is to present several formats based on recursion or based on iterative format. So the overall logic is in order traversal of binary tree. So here, actually, besides solving this problem, we actually emphasized how we write in order traversal for a binary tree in recursive format or in iterative format. And then once you know this, and according to different problem requirements, you can add the specific logics to make the problem solved. So with that said, I guess that's about it for this video. Thank you.